Today we are going to start this video talking about something called an atom. The same atom that we really started with in the first chapter called matter. We said atom was the most fundamental unit of matter. Today we are going to kind of dissect that atom a little bit further and go a little bit deeper into that atom. An atom is essentially made out of what are called protons, neutrons and electrons. They are essentially subatomic particles, and they are called subatomic because they are kind of units below what an atom is. An atom essentially consists of a nucleus, which is where the protons and the neutrons reside together in a dense core. Around that nucleus is a loose set of the other subatomic particle, which we call electron, which kind of goes around in circles around this nucleus. The nucleus and the electron cloud, as we call it, forms what is an atom. That picture of an atom was something that was given by the Rutherford's atomic model in 1911. The nucleus consists of protons, which are positively charged, neutrons, which do not have any charge, and electrons, which are negatively charged. But the number of protons is exactly equal to the number of electrons in an atom, and therefore the atom is neutral in charge. The fact that the number of protons is equal to the number of electrons also kind of leads to the fact that if the atom were to stay as an atom, it would always have the same number of positive and negative charges. And even if in some combinations they were to exchange electrons among themselves, there is always a conservation of charge, of electric charge. Electric charge kind of remains constant in typical process involving atoms, and that's called the law of conservation of electric charge. Now I kind of have to come to that point because what we are really going to talk about today is not about the atom, but it's about another form of energy called the electrical energy. Just like the origin of mechanical energy was the presence of an object at a particular place, like in a gravity, because of its gravitation potential, the whole area of electrical energy comes from having a certain property called charge. How much charge it has kind of decides how much of electrical energy the matter will have. Therefore, for understanding the origin of electrical energy, we need to look back because the origin of electrical energy comes from charge, which essentially comes from an atom with the lack of electrons or the excess of electrons, because the atom per se is neutral, which means the protons and electrons are equal in number. An atom can become positive when it has less number of electrons than it originally had, or it can become negative when it acquires additional electrons from some other source, and therefore the atom becomes an ion and therefore is negatively charged. But way back before electricity was kind of known to come from atoms, it was experienced. One of the first time the electricity was experienced actually goes back to almost 600 BC. I don't know if you are kids and you've done this experiment where you take a comb, rub it on your hair, and then you kind of introduce it to small pieces of paper, and the small pieces of paper kind of stand up and dance around that comb. This was an experiment I remember doing as a kid between classes as we were filling up time. That essentially is a manifestation of electricity or electrical charge. What really happens is when you rub against two objects against each other, electrons are able to transfer in or out depending on which way it goes, and it renders one of the objects positive and one of the objects negative. And then it When you bring it up to small bits of something like paper, it's able to induce a charge, an opposite charge onto it, and then when you kind of bring it up, there is because of the charge, a certain amount of attraction. That is called static electricity, and it was known well before the Rutherford's atomic model of the origin of static electricity or electricity per se. So you have experienced static electricity in many other ways. In dry weather, sometimes when you reach out to the handle of a door or of that of a car, you get an electrical shock. It's a sensation of just something that's passing through your fingers, and it turns out that's exactly the static electricity that's transferring between that object and you. There are many places where you see, so for example, wearing a shirt, sometimes you hear a slightly crackling sound, especially if it's a polyester shirt, which tends to hold a lot of static electricity. So there are very many ways that you begin to see static electricity around you. And that electrical energy is what we are going to talk about in more detail today. But remember, static electricity is something that you occasionally see around in the three examples that I gave you. But another big form of static electricity is lightning. Lightning simply happens because in atmosphere, things get charged, especially the clouds, and then when they develop an excess amount of charge, they just need to dump that charge somewhere. They dump it through a lightning strike, which kind of connects the excess charge and brings them to the ground. And that's how a lightning works. So a movement of static charges in large numbers through, which is essentially a passage of electrons, is called the electricity that we are more familiar with. That's one step to understanding the more familiar electricity. Lightning happens because charges conduct through one place which has more charge to one place which has less charge. Therefore, conduction is another phenomena of transfer of charges. We often say that, copper is a good conductor of electricity. What do you mean by saying that copper is a good conductor of electricity? Copper has the ability to transfer charges from one place to another with minimum resistance, and therefore it becomes a good conductor of electricity. But there could be things like wood or a thread made out of cotton, which really does not help transfer electricity through it. It does not allow for charges to flow through it, and that becomes either a bad conductor of electricity or an insulator. So metals are generally good conductors, and non-metals like wood, cloth, and so on and so forth, rubber, are all bad conductors or insulators. That again fundamentally comes from the matter from which they are composed. Metals have a property of keeping electrons loose, so they're able to lose electrons very easily to the material per se, and therefore a lot of electrons are available to conduct charge, and therefore they are good conductors. You now begin to see the link between the properties that we see at a macroscopic level, like static charging, like conduction, again starting from matter, which was how we started this entire series of discussions. So therefore, how do we then translate this electricity into more useful things that we see around us? We know today that there are these plug sockets around the house, and if you need power, you simply plug the devices into those sockets and they get powered, whether it's a table lamp, whether it's the tube lights, which is internally wired to an electrical supply. The supply then comes from the pole outside our house. So essentially, electricity at home is essentially charges being pushed into our house, just like the municipality pushes water through a pipe. The electricity board generates energy, electrical energy, and then transfers them through these good conductors, which are wires, which you see as overhead cabling, into our house. And because there is a source at the electrical supply company, the electricity then flows through those wires into our house and is capable of doing work. We are going to talk about work because even when we talked about mechanical energy a few times we were talking about the ability or the gravitational potential to do work. So energy and work were very related, and today we are just using electrical energy to do a lot of work. In a heater at home, when you plug it in, the electrical energy gets converted into heat energy, and that's how you're probably able to put a pan of water on it and boil off the water. So electrical energy in our country comes at around 220 volts, and volts is a way of measuring potential. Just like height was an equivalent of measuring gravitational potential. Like, remember, if you recall, mgh was the amount of gravitational potential you had, right? Similarly, the electric voltage is related to the electric potential. So higher the voltage, higher the potential for it to transfer electrons and therefore be able to do work. So we get electricity at about 220 volts and 50 hertz, and we call it 50 hertz because the current that we get is not a steady current. It keeps oscillating from sometimes a plus to a minus to a plus and minus again, and that alternating current comes at 50 hertz. That's the alternation is at 50 times per second, and therefore it's 50 hertz. The AC that we get at home, the alternating current that we get at home is rated at 220 volts, 50 hertz. You will also see in your house there are two types of plugs. The smaller plugs, which have 3 holes, and then another slightly larger plug which have also 3 holes but slightly bigger. The bigger ones you will see around geysers, hot water geysers at home, or around equipment around your kitchen. Whereas the other plugs is where you typically put in your chargers for a phone and so on. The reason they are separated is the smaller one is called a lighting circuit. Essentially means that it can do less amount of work, and the other is called the heating circuit, and it does more amount of work. So the amount of work that it does is not just the voltage at which the current at the potential comes, but the amount of current it is able to deliver. So the smaller circuits are able to deliver about 5 amps of current, and the larger circuits, the heating circuits, are able to deliver about 15 amps of current. So therefore, inherently the power that you get is related to the amount of work that that socket can do. A smaller socket can't do a lot of work and therefore cannot power a geyser which is meant to heat water to, let's say, 60 or 70 degrees for your bathing. That ability to deliver the current, whether it's 5 amps or 15 amps, along with the potential at which it comes, 220 volts, is what defines something called a power of the electrical circuit, which is a product of the voltage and the current. So the 5 amps circuit can at best give you 220 volts into 5 amps, which is around 1000 watts, as against the 220 volts 15 amp circuits, which is able to give more than 2 plus kilowatts or 2000 watts or more. So that's how electrical energy comes into our home. But that's not the only way electrical energy comes. You also note that when the power goes off from the electricity station, you still have a UPS that is delivering power. How does the UPS get power when you're not getting power from your electricity board? We do that because we tap into something called a battery, which is connected to an inverter, which is then connected to electrical circuits. You might have heard your parents say, oh, it's on UPS, don't run heavy equipment. You don't run TVs or you don't run large. You only keep it for minimal needs like lights and maybe a fan. That's because given that the battery source is not so powerful in terms of how much power it can deliver, you don't want to consume it very quickly because then you would run out of power before probably electric supply came back on. Therefore, a UPS is essentially an alternate source of electrical energy, which again starts from a battery. And battery, like we said, is another alternate source of energy which starts out as chemical energy. A battery is essentially a cell added up in series where the voltage of each cell gets added up. And therefore, the fundamental unit of a battery is a cell. And that cell has a little chemistry going on there that continues to drive conversion of chemicals within that battery to help power a voltage and a current that's then taken in by your UPS and converted from what is called a direct current, which I didn't speak about. A battery provides direct current. The inverter actually takes that direct current and converts it into alternating current at 220 volts, 50 hertz, so that your house can be powered, house electricity can be powered starting from a battery. So that's how you see that electrical energy starts off as just electrons and the ability for electrons to move because of a potential difference, an electrical potential difference, and that flow of electrons is essentially a current, and that current is what does work. It can do work in terms of going through a resistive wire and helping the matter inside, the atoms and molecules inside, to vibrate faster, generating heat, which then transfers onto your copper vessel on which there is water, which then gets boiled up. So the last form of energy that I wanted to speak about is electrical energy, and you see how useful electrical energy is. You can't really think of a device that cannot be powered without the electrical energy in your house. Even if it were batteries, which is again chemical energy getting converted to electrical energy. For example, in the headsets that you wear, they really have no power coming in, but it's the batteries inside that keep it powered. And when those batteries drain, you kind of have to put it back into electrical circuit to recharge them through a charger. That's what you do with your mobile phone batteries too. This is something you are very familiar with. So this was really the last form of energy that I wanted to discuss with you. This also is probably the last unit that we need to talk about in terms of the various forms of energy. We talked about heat energy, we talked about light energy, we talked about sound energy, and here we are talking about electrical energy. But remember, all of these are just various forms of energy, and energy fundamentally is stored in the potential of atoms, whether they are solids, liquids, or gases, and those intermolecular forces between those various molecules in an element or in a molecule that really brings about all of these various forms of energy. To me, that is the wonderful link of studying through the course of physics for class 8. The various units may look unconnected, but remember, it all started with matter. It started with the atom, it started with the elements, it started with compounds, started with molecules, and then we beautifully went about saying, where are those macro properties that we see? The macro properties of light, of scattering, of how you visualize things, how you hear things. All of that is fundamentally coming from energy, which again has its origin in matter. I have really enjoyed doing this series of videos. I think it's now about 8 videos or 9 videos talking about the various forms of energy and the various forms of matter. And I hope you learned through these courses or these classes that they are all ultimately linked to a really nice story around the subject of physics. I'd also promised that I'd cover the entire syllabus of class 8 through these lectures, and today happens to be the last of the series, and also happens to be really the end of the year. I had promised to do this by the end of December, and I'm stuck to the promise with just about a day to go. So this is really thanking you all, my audience, for enjoying these videos, commenting on it, and coming back to me, including my colleagues who've been really graceful to review some of these and give me their comments. So thank you, my student community. Thank you to my colleagues and professional friends. And with that, I'm signing off on these learning physics modules. And I also want to end with wishing you all a wonderful 2020, where you have great opportunities to learn and of course move on to the next class, which will be class 9 for all of you. Thanks again, and see you all again in probably another conversation on another topic. Thank you and bye.